In this video, we are going to be discussing the concepts of electronegativity, bond polarity, and molecular polarity because we are going to be discussing VSEPR rules. So, the first thing that we're going to talk about is electronegativity and bond polarity. Understand that electronegativity is one of those trends in the periodic table that you guys need to know. Electronegativity is a particular value that has been assigned to elements in the periodic table. In this value for a particular element is going to indicate the attraction of an atom for the shared electrons on a bond. The higher the value, the more electronegativity an element has. The most electronegative atom is fluorine with a value of 4.0. Now, understand that the trend in the periodic table is that electronegativity, if I zoom in to the trend, increases as we move across the period from left to right, and it decreases as we move down within a group. Understand that these values, you guys don't need to memorize them. There is a periodic table with values for electronegativity for the elements in the periodic table in the reference sheet for exams that has been posted on Canvas. Now, understand that electronegativity is high for nonmetals, okay? Because remember, fluorine is the highest, and it tends to be low for metals. And you can see that by looking at the numbers. Now, why is it important to know electronegativity? Because electronegativity can actually define what type of bond is going to exist between two atoms. So for example, here we have three different compounds. Now, for the first one, which is where chlorine is bonded to chlorine, I'm just going to include the electrons. This is diatomic chlorine or molecular chlorine. You can see that in this molecule, okay, is we have chlorine attached to chlorine. And if we look at the electronegativity values, okay, for chlorine and chlorine, when we subtract them, because the difference has a value of 0, then that means that this bond, okay, that I am circling in gray is going to be a nonpolar covalent bond. Okay? So anytime you take the electronegativity difference between two elements and it is between 0 and 0.4, that means that you have a nonpolar covalent bond. Okay? Let's look at the next example, HF. So what we're trying to define is that in HF, this is the Lewis dot. And we're trying to define what type of bond is this one that I also highlighted in gray. Okay? So all we have to do is look at the values for electronegativity. 4.0 is the one for fluorine. 2.1 is the one for hydrogen. So when we subtract those two numbers, the difference in electronegativity has to be a positive value, never negative. So because the difference in electronegativity values between the two atoms is 1.9, then that means that that bond specifically is a polar covalent bond. Okay? So anytime you take the difference between two atoms and the value is higher than 0.4 up to 2.0, then that means that we have a polar covalent bond. Let's look at our third example. Here we have sodium and chlorine. Okay, we already know that sodium chloride is an ionic compound, but actually let's define this ionic bond. And remember, the ionic bond should never be written with a line. It's just the positive charge on the sodium. The chlorine is negatively charged. So technically, this is how we illustrate an ionic interaction or an ionic bond between these two elements, if we look at the electronegativity difference between chlorine and sodium, okay, then we notice that because it is 2.1, what is unifying them is an ionic bond. So anytime you have an electronegativity difference higher than 2.0 up to 4.0, then that means that we have an ionic bond. Now, there is something that is very important. If you have a polar covalent bond, understand that for a covalent bond, there's different ways in which we can illustrate it. Because a polar covalent bond, understand that because of the separation of the charges, okay, we have created a dipole. Dipole simply means that you have a positive end and a negative end. And this is only used for polar covalent bonds. We are going to be illustrating this dipole by one of two symbols. We can illustrate it by using a lowercase Greek letter delta, which is this, in which the delta, I'm just going to do it for the carbon-oxygen bond. The delta minus is going to be placed at the atom that is going to be more electronegative, and the delta plus is going to be placed at the atom that is less electronegative. So if we look at the values for carbon and for oxygen, as you can see, carbon is 2.5, oxygen is 3.5. In terms of the electronegativity. So that's why we illustrated it as carbon with a delta plus and oxygen with a delta minus. Now, understand that there's another way in which you can illustrate a polar covalent bond. And again, it's polar covalent, right? Because the electronegativity difference is 1.0. So we can also using an arrow pointing from the positive to the negative end can also illustrate that dipole. So as you can see, this is what this arrow is illustrating. Now, why is this important? The polarity that is present in a bond, it can help us understand what are overall going to happen in the context of these molecules being present as a whole in a Lewis structure. So again, this is only utilized for polar bonds, and we know how to determine the type of bond by looking at electronegativity differences. Okay, so the next topic that we're going to cover is shapes and polarity. And when it comes to shapes, understand that whenever we have covalent compounds, we are going to have these molecules adopt a geometry. Okay, and this geometry basically comes from the idea that the atoms have electrons, and because like charges repel, they are going to adopt a geometry such that those electrons are very far away from each other. Okay, so to give you guys an example, this is methane. It adopts a tetrahedral geometry. It has a tetrahedral shape, which means that the angles in between all those hydrogens, okay, so these guys are the hydrogens, and this is the carbon atom, is going to be 109. And as you can see, the third representation is just how we draw the 3D structure, okay? All of these ideas come from VSEPR theory. And VSEPR stands for valence shell electron pair repulsion theory. So the long story short of what VSEPR theory is that it describes the orientation of electron groups around the central atom. So basically it explains how these geometric structures for covalent compounds arise. So in order for us to understand VSEPR theory, we need to understand what is an electron group. And remember that electron groups are going to be defined as what is surrounding our central atom in a Lewis structure. So when it comes to electron groups, there are four different things that can be constituted as an electron group. Okay, so a lone pair is one type of electron group. A single bond is one type of electron group. A double bond is one type of electron group. A triple bond is one type of electron group. So as you can see, there's four different types of electron groups. So let me give you an example. So as you can see, here we have NO2, and in this molecule of NO2, understand that overall, as you can see, we have around the central atom, which is nitrogen, 3 electron groups, okay, which are the lone pair, the single bond, and lastly, a double bond. Again, each one of those constitute one electron group. So, when it comes to VSEPR theory, understand that from table 6.16, what you guys mainly have to focus is on the electron groups for a particular molecule, electron group geometry, bond angle, and molecular shape. These are going to be the main things. Now, understand that molecular shape is going to be dependent on the number of bonded atoms and also the lone pairs. So it is important that you know how to read this table when you're trying to determine the electron group geometry for a molecule, its bond angle, and its molecular shape. So, in order to practice all of this, I'm going to start by doing a particular example. So, as you can see here, I'm going to do letter A. So for letter A, I'm going to draw the Lewis structure. Carbon is my central atom. This molecule has 2 hydrogens and 2 fluorines. Okay, to draw its Lewis structure, it looks as followed. Okay, so to determine the shape of the molecule, I'm going to determine the electron group geometry and also the molecular shape. When it comes to questions in the exam, remember that I will explicitly ask you which one is the group geometry or the electron group geometry and what is the molecular shape. So make sure that you read the question carefully. And then we're going to determine the appropriate bond angles, okay, for that particular molecule. So as you can see, if we focus on the carbon, this carbon atom has 4 electron groups. 4 electron groups come as 4 single bonds. Okay? Let me just redraw this fluorine so it's a little bit more obvious. So, when it comes to this carbon atom, when I'm trying to determine the electron group geometry, understand that I will look to my table and I will say, oh, for 4 electron groups, my electron group geometry is tetrahedral. Okay? It doesn't matter how many attached bonds and lone pairs you have, anything that has 4 electron groups is known as tetrahedral. So I will write here tetrahedral. Now, because this first molecule doesn't have any lone pairs, meaning any dots on that central atom, when it comes to molecular shape, going back to my table, I will say, okay, This has 4 bonded atoms, no lone pairs. That means that the molecular shape is also tetrahedral. Anything that is tetrahedral, as you can see in here, has an angle of 109. So the angle for those bonds are going to be 109 degrees. Okay? Now, one more concept that you guys need to master when it comes to this is the whole idea of overall polarity of a molecule. When it comes to this slide, I want you guys to focus specifically on what are these representations. Let me just do them in different colors. For non-polar molecules. Let me start again. I want you to focus on these. The reason why I want you to focus on these is because the one in green, this is what makes a linear molecule nonpolar. Okay? And for a linear molecule to be nonpolar, it needs 2 identical groups on either side. The one in purple, these are the rules for a trigonal planar molecule. And what I mean by this is going to be those words, linear, trigonal, planar, and the next one, which is tetrahedral, is because we are looking at electron group geometry for a particular element. Okay? So, as I was mentioning, the one in purple is what makes something that is trigonal planar nonpolar, which means 3 identical groups, okay, will make a trigonal planar molecule nonpolar. Now, if we look specifically at a tetrahedral molecule, we need 4 identical groups in order to make it nonpolar. Okay, so I'm going to utilize as examples, okay, just a series of the things that we have already answered, and we have their Lewis structures. So going back to the first example that we build our Lewis structures, okay? So if we go back to here, as you can see, that H2S molecule, if I determine its electron group geometry, okay, this is going to be tetrahedral. Because it has 4 electron groups. What are the 4 electron groups? 2 lone pairs and 2 single bonds. Then I ask myself, okay, if I look at sulfur, does it have 4 identical groups? The answer is no. So that means that this molecule is polar. Let's look at SO3. When we're looking at SO3, understand that here we have 3 electron groups around the sulfur. So that means that this molecule is trigonal planar. Okay, the 3 electron groups are going to be the lone pair, the single bond, the other single bond. Let me just erase these arrows. Now, this molecule, understand something, that when I mean identical, that doesn't mean that when you look at it, it is the same. It just means for overall polarity. Identical means same attached atom, not the type of attachment only. Okay, so when it comes to SO3, as you can see, this trigonal planar molecule is attached to, I'm just going to use a different color highlighter, is attached to an oxygen atom, attached to an oxygen atom, and then this one, even though it's a double bond, that is still attached to an oxygen atom. So that constitute 3 identical groups. Overall, SO3 is a non-polar molecule. If we look at the last Lewis dot that we did, as you can see in CH2F2, this is a tetrahedral molecule with the groups around the central atom are not identical, so this molecule is polar. Make sure that you practice determining the overall polarity of molecules by utilizing the resources of the textbook, the worksheets, and also the SI worksheets that are on Canvas.